In this lecture, let us talk about suppressed sideband modulation. Till now, we have looked at DSB-SC, then DSB-AM with carrier, amplitude modulation with carrier, and quadrature amplitude modulation. And we have discussed the pros and cons of all these modulation schemes. Okay, particularly in DSB-AM, efficiency is very less. Okay, efficiency is less, and also bandwidth also 2 times of your message signal. Now one can ask a question: is there any way to increase the bandwidth utilization and also increase the efficiency? Now if you look at the spectrum of your DSB-SC signal X of f, then you have the sideband like this. Sorry, the figure is something wrong. Like this. Now let's say this is my center frequency of C, and this one is upper sideband and this one is lower sideband. Now in terms of information content, both your upper sideband and lower sideband carries the same information. So there is no need to transmit both the sidebands. Either you transmit upper sideband and remove the lower sideband, or transmit lower sideband and remove the upper sideband. So this type of modulation is called suppressed sideband modulation. So now you can remove the sideband either completely or partially. Okay, so there is another choice that is given to us. Either you can suppress completely or partially. Here you can ask me, why are we giving these two options? Because there are pros and cons on each of them. Okay, sometimes we cannot suppress it completely, but we can ask, can we suppress partially, so that we can save some amount of bandwidth. In some cases we can suppress the sideband completely. Okay, so we will see some examples for both the cases as we go along. So when we suppress completely, it is called a single sideband modulation. Single sideband modulation. If you suppress partially, then you can say vestigial theorem, and this theorem is called by the name of single vestigial sideband modulation. VSTE, this is not I, okay, VSTEGIAL, vestigial sideband modulation. Okay, this one is called Ssb and this one is VSB. So there are two types of modulation in suppressed sideband modulation operation. Now let us first discuss single sideband modulation. Single sideband modulation. So in short we say Ssb. To generate a Ssb modulation, do the following. What you need to do is first generate a DSB-SC signal. Okay, so how do you generate DSB-SC signal? You take m of t and give it to a product multiplier, and the other input is your carrier component a suffix c times cosine of omega ct. And what is this? DSB-SC. Okay, and somehow what you do, you filter the sideband, any one sideband. So therefore I put a sideband filter. Either you remove the upper sideband or lower sideband completely. Okay, now let me call x of t. This is the modulated signal. I mean single sideband modulated signal. That's it. Okay, so now we want to remove any one of the sidebands. Okay, so you have to have some kind of filter such that it removes any one sideband. First look at the whole thing in the frequency domain, okay? Instead of talking about in the time domain, let us look at the whole thing in the frequency domain. Let's say my spectrum is like this. In order to differentiate, let me say my spectrum will be like this. This is my M of F. Like this. This is frequency and plus B and minus B, and this is 0. Okay, this is my message signal spectrum. And once you do the modulation, then it will be like this, and this side also like this. Okay, so this is the spectrum of your DSB Ssb modulator output. Now after passing through the sideband filter, we are retaining only the upper sideband. Okay, so what you do is you put a sideband filter, and that filter pass along this guy. You put a filter like this. Okay, this will be passed and this will be rejected. And here also this will be passed and the lower sideband will be stopped. Okay, that means if you retain the upper sideband, what will you do? What kind of sideband filter you should have? The high pass filter. Okay, put a high pass filter like this. Put a high pass filter like this, like that. Or you can put as per the red line, you put a band pass filter, or you can put a high pass filter. You can use any one, and you can retain the upper sideband and reject the lower sideband. Okay, so therefore the high pass filter or the band pass filter only passes this upper sideband portion of the spectrum and reject anything else. Theoretically, a high pass filter will do that. In practice, of course, the band pass filter will do. So theoretically, high pass filter would be able to separate out the upper sidebands from the lower sidebands. So we require a filter with this kind of characteristics. Okay, so like this kind of characteristics, like that. So what is the transfer function for this kind of characteristics? If you write down h of f in the frequency domain, h of f is equal to 1 for f is greater than fc for positive frequencies, and f is less than minus fc, and 0 otherwise. So if you want to write in more compact form, then h of f is equal to 1 where mod of f is greater than fc, and 0 and mod of f is less than fc. That's it. Okay, so if you want the lower sideband, you should have a low pass filter with a cutoff frequency of fc. So depending upon whether you want the lower sideband or the upper sideband, you can use appropriate filter, which ideally could be low pass filter or high pass filter. In practice, we don't use low pass filters of such a large bandwidth. See, let's say this is the carrier frequency, let's say 1000 kilohertz. In case if you want to retain the lower sideband, then you put a low pass filter like this. So this is very, very large bandwidth for the low pass filter. So we will not use a low pass filter, and we will not retain the lower sideband. Generally, we will like to retain the upper sideband, because realizing such a very large bandwidth of low pass filter is little difficult. In many cases, the signal m of t has a finite small bandwidth. Okay, that bandwidth is this much. Finite small bandwidth. That's it. So it is more convenient to use band pass filters instead of using this kind of high pass filter. You use a band pass filter. Let me draw the band pass filter here. So this is my band pass filter. You can use band pass filter like this. So I have 3 filters. Either you can use a low pass filter, or this one is high pass filter, and this one is band pass filter. That's it. Okay, but for a theoretical discussion here, it is preferable to think in terms of high pass filter and low pass filter. So in our discussion, either we discuss in terms of low pass filter or high pass filter, not in terms of band pass filter. But in practice, you can choose any one. Okay, let us assume that suppose we retain the upper sideband. Okay, so let me draw again. So I have the like this. Let me draw in the dotted line like this, and like that, then dotted line. This is my upper sideband and lower sideband. This is lower sideband, and this one is upper sideband. So I would like to retain the upper sideband and reject the lower sideband. How do I do that demodulation? In case if that is the case, now how can I go about demodulation? Because if I cannot demodulate these things, then this whole exercise is a wasteful exercise. Okay, it does not help anything. Okay, whatever you do in the demodulation, provided that you should demodulate on the other side also. If you are unable to demodulate, then it is a wasteful exercise. Okay, so again the demodulator remains the same. Okay, we use a synchronized demodulator that we had for DSBSC. Absolutely no difference. Convince yourself. Same signal you are transmitting, but what happens, only one sideband you are removing, that's all. So what I am saying is, as far as demodulation is concerned, take your modulated signal x of t, give it to a multiplier with the frequency of a times cosine of omega ct, and give it to low pass filter. That's all. Same kind of. This is your message channel m of t. Absolutely same. Okay, so look at it in the frequency domain. It should become obvious. Okay, when you multiply by cos omega ct, then this portion will come here and this guy will come here. Maybe I'll use some other color. If you multiply by cos omega ct, then what happens? By frequency translation property, this portion will come here and this portion will come over there. Again you will get back your message signal like this. Okay, very simple operation. Okay, so we are carrying out frequency translation by minus fc and plus fc. Okay, so you get the baseband spectrum which is like this. After demodulation it becomes like that. Okay, so the plus fc component comes over here. This is plus fc and this is minus, sorry, this point is minus fc. I'm sorry. This point is plus fc and this point is minus fc. So this minus fc component will come over here and plus fc component will come over here. So you get the baseband spectrum. Okay, what you wanted. So there is absolutely no difference in the demodulation process. It remains the same. So the demodulator remains exactly the same that you had for the DSBSC. Just apply the frequency translation process or frequency translation theorem on this modulated spectrum, and you see that your baseband spectrum comes back along with the component. This is plus b and this is minus b and this is your m of f. Absolutely no difference. In fact, you'll get one more component here at around 2 Fc. Anyway, that we don't want, right? That will be removed by the low pass filter. And one more component you will get at 2 Fc because of the frequency translation. Okay, so the same argument you can repeat when you retain the lower sideband rather than the upper sideband. Okay, so please convince yourself that if you retain the lower sideband and transmit, if you retain the lower sideband and transmit the upper sideband, once again the same demodulator would reconstruct your message signal back. Okay, so whether you are transmitting the upper sideband or the lower sideband or the double sideband, your demodulator will be the same. Same demodulator can be used. Same synchronous demodulator is used for transmitting upper sideband okay, and rejecting lower sideband. Similarly, transmitting lower sideband and rejecting upper sideband, or transmitting both the lower sideband and upper sideband. Same synchronous demodulator will be used. Okay, so please convince yourself. So the practical realization would require a suitable sideband filter. Okay, now this designing high pass filter or low pass filter or band pass filter is not a trivial option that you want to do. Okay, that is what you want to understand in this process. Okay, you require a sideband filter with almost ideal characteristics, right? So if you look at the sideband filter here, when I say, if you enlarge, see it has a sharp cutoff like this. It goes like this, or it goes like this, or it comes like this. So this kind of sharp cutoff ideal low pass or band pass or high pass filter is not a trivial job. It's not a trivial option that you want to do. Suppose you decided to retain the lower sideband. Let's say, let me draw again one more time, because this is a little confusing topic. You have like this. Okay, suppose you decided to retain the lower sideband and remove the upper sideband. Let's say you do it through a low pass filter. Okay, so you put a low pass filter like this and retain the lower sideband. This is my lower sideband and this is my lower sideband. Okay, so I should have this kind of this kind of characteristic function or transfer function. So the transfer function should have a perfect transmission up to the carrier frequency Fc minus Fc, and here up to frequency Fc. It should have sharp cutoff. And you might have studied this in your from electronic circuits. It is very, very difficult to realize a filter with a sharp cutoff. Okay, I mean it should transmit up to the carrier frequency Fc and reject completely after Fc. We know that such ideal low pass filter is almost impossible to realize. Very, very difficult to realize. In practice, of course, you will not realize a low pass filter with such a huge bandwidth. Okay, you will realize a band pass filter. What you do? You put a band pass filter like this, and yeah, here also put like this band pass filter. So one can approximate such a filters. Okay, basically you require what is called a high Q tuned filters. So this kind of characteristics will be given by high Q, high quality factor, tuned filters. So if at all if you want to, then you should have high Q. High Q means very high value. Okay, basically you require typically these frequencies plus FC, then minus FC, FC plus B, okay, which are very high, and this bandwidth will be very small. See, suppose FC is equal to 1000 kilohertz, I mean 1 megahertz, bandwidth let's say 4 or let's say 5 kilohertz. Then what is the bandwidth? Bandwidth is equal to 10 kilohertz, but carrier frequency is 1000 megahertz. So therefore this is narrow band. Bandwidth divided by your center frequency FC is less than 1, then you say that is narrow band. Okay, so you require typically very high carrier frequency and a small fraction of the bandwidth. So that will be very small fraction of the carrier frequency. So this requirement is realized by a narrow band high Q tuned filters. Okay, this is called a narrow band. This is realized by narrow band high Q tuned filters. Okay, that will do the job. We know the quality factor of the tuned circuits. Q factor determines how much bandwidth you have around FC. The larger the quality factor, the lower the bandwidth. So a large quality factor tuned circuit have a very sharply tuned filter. For ideal tuned filter, Q has to go to infinity for ideal filters. When Q becomes smaller and smaller, the bandwidth increases. It will not be ideal low pass filter or ideal band pass filter. So you require a suitable Q value, otherwise you cannot realize it. Generally for communication we need a very high or very sharp cutoff filters. When I say low pass filter, it should be like this, but in practice the low pass filter will be like this. Okay, this is practice, this one is ideal. So this kind of things I don't want. Okay, so to realize now I am very sharp cutoff, then we need high Q filters. So designing a high Q tuned filters using conventional passive components like inductors, resistors and capacitors is extremely difficult. Why? Because they would be typically very large order of filters. Remember, no matter what you do, how ideally you construct your inductors or capacitors, inductors and capacitors, there will be some loss in the inductors and there will be some loss in the capacitor. These losses are due to the resistance of the inductor or various kinds of losses in the capacitor, and these losses reduces losses reduce the quality factor. So if you do not have these losses, you can have the ideal tuned filter, no problem. Because of these losses, the frequency response gets flattened and we do not get a very sharp filter. On the other hand, there are materials which enable the realization of this high Q filters, namely a quartz crystal. Okay, I will just simply mention the name here. It has very nice electrical properties. You can use quartz crystal, and interestingly it has some useful electrical characteristics, and it can be used in the resonant circuit, RLC resonant circuit of tuned circuit to provide a very sharp responses. Okay, here I just wanted to mention this fact, and I don't want to get into this discussion on how quartz crystal work in this connection. So you can get the kind of filters that you want to design for the Ssb generation by using quartz crystals. So one can use a specially designed or properly designed quartz crystal filters, which have very interesting properties. Okay, this very interesting properties of providing you very sharp cutoff. Okay, so we will discuss more about this a little later as we go along if time permits. Now before we proceed further, let us ask ourselves like the waveform, how the waveform look like in the time domain at this at the output of the sideband filter. So you have m of t, you can give to the product multiplier and carrier, and the output is DSB SC, and this is given to sideband filter, any one sideband filter. Now we would like to ask this output, how does this output look like in time, or what is the mathematical expression for this output in the time domain. That is what we want to address now. Okay, that means, can I write a mathematical equation? Can I write a mathematical equation for this? That is a question. Okay, the answer is not that easy anymore. Okay, it is not that much easy. See, up to this point, no problem. You can write m of t times cos omega ct. You put a here, no problem. A. But here it is very difficult. So we need to bring into Hilbert transform and many more things. Okay, in the frequency domain, product of two waveforms. What is the kind of waveform can I have after sideband filtering? It is not so obvious in the time domain. Okay, so we will take up that in the next lecture. Okay, how we can write down the mathematical expression for the output of your sideband filter. Okay, there is another method. Okay, of still there is one more method for generating the Ssb signals rather than your tuned filters. Now one can ask a question, why do we need a single sideband modulation? What is the problem if I use both the sidebands? The first point is, you can save the bandwidth. You can save the bandwidth. If you save the bandwidth, then what will happen? See, in the frequency axis, let's say this band is allotted for, let's say, user 1, U1, and this portion is empty, so you can allot for user 2, and again this portion is empty, you can allot for user 3, and so on and so forth. Okay, so I can put another message in this bandwidth, another message in this bandwidth. So when I discuss frequency division multiplexing, this is precisely what we can do. So this is called frequency division multiplexing. So there are advantages, okay, that you derive from Ssb. So because of this Ssb, you can put or you can pack as many message waveforms as possible using Ssb modulation. You can put different messages, and each of them occupies only, what is the bandwidth? B hertz, exactly B hertz. It is not asking you much more bandwidth. Okay, I can put one message here, one message here, one message here, and another third message here, and so on and so forth. Okay, so I can put them side by side at a spacing of only B hertz. B hertz. So there are some methods available to do that. Okay, so let me stop at this point. So let me stop at this point. The next lecture we will continue. So that is the advantage of Ssb modulation. Okay, so in the next lecture we will start to discuss how do we represent the single sideband signals at the output of your sideband filter. Okay, so let me stop at this point.